This video is part of my mini-series on techniques that use framebuffer objects in WebGL2, and today we'll be looking at Bloom. I was originally inspired to make this tutorial years ago now because of a couple of YouTube videos by the Cherno. In them, he had some pretty unkind things to say about a bunch of OpenGL Bloom tutorials, which he says get the effect completely wrong. And he goes on to explain how modern Bloom is implemented by most AAA game publishers and popular graphics engines. I'll link to the videos so that you can watch them yourself, but I thought it would be fun to implement this kind of Bloom from scratch in WebGL. Again, there won't be any live coding in this video, but the final code is linked in the description. My implementation is probably fine, but the code itself is not meant for production. I've written it so that it's linear and simple to follow as much as I can. So hopefully you'll be able to take what you learn here and write this yourself in a way that makes more sense to you. In addition to Bloom, this video covers a bunch of other things that we've not covered before: HDR texture storage, downsampling and upsampling, and tone mapping, plus a little bit on gamma correction. Also, here there will be a couple of examples of fixed Gaussian blur using single-pass bilinear kernels, which is something that I missed in my video on variable Gaussian blur, so there's actually a lot of cool stuff in this one. When I was 11 years old, I saw the original Star Wars in the theater. It wasn't Episode 4 yet, just Star Wars. And I remember quite clearly what the original lightsabers looked like. 100% rotoscoped, not much color to speak of, and no bloom. In fact, in its original theatrical release, that movie had remarkably little bloom by today's standards. And for sure, those 1977 lightsabers had no bloom at all. Things have evolved quite a bit since then, and these Star Wars posters perfectly illustrate what good modern bloom is supposed to look like. The white-hot core that you see at the center of the blades may seem to be very slightly red or blue, at least they do to me, but they're not. They're both nearly perfectly white. And around that each has a blurry monochromatic halo. This is what modern bloom has come to look like, and this is the effect that we want to recreate. In WebGL, Bloom is a pretty lengthy process and surprisingly expensive. The version that we're going to implement today requires more than a dozen draw calls and about as many framebuffer objects and textures, though there are a few ways that you can cut that down a bit if you want. On the other hand, we're using a small fixed single-pass Gaussian blur, so if you want greater control, you could move to a variable two-pass Gaussian blur, like we looked at 2 videos ago. That'll mean even more draw calls. So yeah, this is not a cheap effect, but if you have the budget, it's well worth it. And it's fun to learn. So how do we bloom? Here's the workflow. Render the geometry, anti-alias, filter out the darker bits, blur and downsample several times, saving the result to each pass, and then add together each of those downsample passes, blurring and upsampling as you go. Add back the geometry, and finally tone map and gamma correct. See, I told you, it's a lengthy process. Before we get into the details, let's go over some of the important new concepts here. Downsampling is easy enough. We just render to a smaller framebuffer object than the texture we started with. The great thing about this is that each time we repeat that, the draw call itself gets much faster. Downsampling to a texture that's half the width and half the height cuts the number of fragments, and therefore the number of times the fragment shader has to run, by 75%. Upsampling goes in the reverse. So yes, rendering to a framebuffer twice the width and twice the height does mean running the fragment shader 300% more often. But even here, there's a performance advantage because the input textures we're sampling from are all downsized. The memory they occupy is much smaller, so the GPU has to do far fewer fetches from memory than it would with full-sized textures. Now, it's very common to add a slight blur when doing upsampling because otherwise you get very obvious artifacts. However, blurring and downsampling are often done together too to produce an extremely strong blur that might have taken hundreds and hundreds of samples to produce otherwise. And in our case today, we'll not be doing a bunch of downsamples to produce a single super strong blur, but a series of progressively stronger and stronger blurs that we can add together. When we work with regular texture storage. Each red, green, blue, and alpha color component value is usually restricted to between 0 and 255, or let's be more accurate, between 0 and 1 with 256 levels of intensity or brightness. Want to add red to this? Too bad. Red's maxed out, and anything that you try to add will just get clamped back to 1. Move to high dynamic range, though, and now you can store color component values much greater than 1. Why does this matter? Well, if this is orange, then maybe this is super bright orange. But thanks to clamping, it's white, with no hint of orange left. Any useful color detail that used to be there has been lost and cannot be recovered. With HDR, it's always there, and color detail is never lost. It is possible to imitate HDR storage using the regular texture formats that we usually work with, but this shouldn't be your first choice. Instead, just use floating point texture storage. This does mean that you have to load the color buffer float extension, but it's so widely supported at this point that that's rarely a problem. Do that and you'll have a fair amount of choice over what kind of floating point storage you can use. In this video, I'll be using this as the floating point storage format, except for not having a negative bit, so no negative color component values. This does follow all of the IEEE 754 floating point rules and behaviors, and it manages to store all 3 RGB color channels at once using just 32 bits in total. We sacrifice some precision, but our new RGB textures take up the same amount of room as a regular RGBA texture that we usually work with. Tone mapping as it relates to bloom is much more complicated than I expected when I started making this video. It may also end up being the one that you'll spend the most time tweaking to get just right. So let's just start with the basics. We have a floating point texture. It's capable of storing both standard dynamic range content with color values between 0 and 1, and HDR content with color values greater than 1. Our buffers are fine with that, and our shader programs are too, but our displays? Maybe, but usually not, and not without a lot of extra work. No, usually anything greater than 1 will get clamped back down to 1, so we have to find some way to avoid that clamping. And we do that by taking that regular color data and the extended HDR color data above it and squeezing it all down into the original SDR region of 0 to 1. This is called tone mapping. A critical problem with tone mapping is that no matter what you do, you have to sacrifice somewhere to make all that extended brightness range fit. And that means elements of your image may appear darker or more desaturated than it used to be. Maybe not by much, but that is a problem. If you're done with your bloom effect and turn it off and turn off tone mapping along with it, the user will probably notice. So, 2 things. First, unless you're very lucky, tone mapping may need to be a permanent part of your rendering process, independent of your bloom filter. And second, it's important to pick the correct tone mapping curve to minimize any negative effect the darkening will have on your output. If you've seen any tutorials or articles on tone mapping before, you may already know the main choices: Reinhardt, Aces, Filmic, Uchimura, and many, many more. Which one should you use? Honestly, try out a bunch and see which ones you like. One tip though. Most of the stuff I do starts with non-photorealistic, low poly, and mostly standard dynamic range renders. And what I've found so far is that the cinematic tone mapping curves like Reinhardt and Aces look absolutely awful. Instead, I found that much more aggressive curves look much better. Uchimura seems to work best for me, though it is pretty expensive. HTAN, the hypertangent function, is also pretty good, and there are some fast approximations that make it extremely cheap to add to your fragment shader. And when tweaking a tone mapping algorithm, I've found that it really helps to use a graphing calculator to understand what your modifications will do to your tone mapping curve. Don't just dump random numbers into your fragment shader and hope to get lucky. If you're using Reinhardt, Aces, or any of the more cinematic HDR tone mapping algorithms, then a final step is usually to do gamma correction. This will re-brighten the image after tone mapping darkens it. This step is usually done immediately after tone mapping in the same shader. The calculation is simple. You just raise the color value to 1 over some constant called gamma. If you've ever calibrated a monitor, you might remember 2.2 is the standard gamma value today. Interestingly, there used to be an all-out holy war between designers over this value. Designers on Windows mostly preferred 2.2, designers on Mac mostly preferred 1.8, and Windows won. So use 2.2 or 1.8? Well, try both. Try 1.2 or 3.0. For photorealistic output, I suspect that you'll find that you don't have a crazy amount of room to play, but for everything else, go nuts and see what works. Or don't do gamma correction at all. If your tone mapper gives you the right output, there's no need for this extra step. Okay, so those are the new concepts we should understand. Now let's go back to our Bloom workflow and add some detail. Step 1, we render our geometry to a texture attached to a framebuffer object, just like always. Step 2, we anti-alias. Well, technically, I guess this is part of step 1. Instead of rendering directly to that first framebuffer object, which we'll still use, we'll render to a multi-sample framebuffer object instead. Bind that, render, and then blit, copying our color data from the multi-sample render buffer to that first framebuffer object. If you're not sure how to do this, check out the last video where I covered all of this. By the way, if you wanted a perfect use case for using WebGL's built-in multi-sample anti-aliasing, this is it. No more jaggies and no added artifacts at all. It's perfect. Step 3, extract the color data that you want to bloom. This could be anything with a luminance value above a certain threshold, hence the name, or it could be particular colors in your geometry that you want to glow, or it might be anything that passes a stencil test, or it could be that you want the whole thing to glow, like maybe this is a particle effect that you'll overlay on top of something else later on. Whatever it is, what we need at the end of this step is a texture containing only the content that we want to bloom. Step 4 is the fun part. We downsample and blur. Take that texture from our threshold pass and render a blurry copy of that to a smaller framebuffer object, one that's a quarter the size of the original, so half the width and half the height. Then do it again. Render a blurry copy of that blurry copy to a smaller framebuffer object, a quarter of the size again, so 1/16 the original size. Then do it again, a blurry copy of the blurry copy of the blurry copy to a smaller framebuffer object that's a quarter of the size again, so 1/64 the original, and so on. The further you go, the less expensive it gets, and the blurrier the output becomes. Where do you stop? No, that's up to you. Also, how to blur is up to you. You could do a two-step variable Gaussian blur, like we covered a couple of videos ago. This will mean even more draw calls, but an important benefit is instead of needing a separate texture for each downsample step, you can use mipmaps to write to a specific mipmap level. That way you only need two textures in total for downsampling, one horizontal and another vertical. In the code today, I've decided to go with a single pass 13 sample bilinear Gaussian blur. It won't be as flexible, but it should be faster. And at the end of this step, we should have a stack of increasingly small, increasingly blurry textures. Step 5, we add up that stack recursively. And when I say add, I don't mean blend them equally or take a weighted average. I mean add with a plus sign. This means we'll quickly blow past 100% brightness doing this, so if we weren't already using HDR texture storage, we'll need it now for sure. In the first upsample pass, grab the smallest downsample, blur it, and add that to the one above it. We'll output this to a framebuffer object that is the same size as the bigger downsample texture, but twice the width and twice the height of the smaller one, which is why we consider this upsampling. Then take that output, blur it, and add it to the next downsample above, and output that to a larger frame buffer. Then do it again and again until all the downsample textures have been added together. At this stage, you'll have your bloom, but nothing else. Also, your last output should be half the width and half the height of your original full-sized render. So, in your very final upsample step, take that last result, blur it, and then add it to your original anti-aliased geometry texture. Now things mostly look like a proper bloom effect, except a lot of our color detail is in the HDR region, which will get clamped when we send it to the canvas. So step 6, we tone map, and maybe gamma correct if necessary. Do that, and at this point, the bloom is complete, and you can either output to the canvas or to another regular non-HDR frame buffer object. Either way, you're done. I really hope that makes sense. Go to the linked JavaScript file in the series GitHub repo so that you can follow along. This file has almost everything in it that you need. You'll need to have GL matrix loaded somehow into the page. This is the scene that we're going to apply the bloom to. I won't go into all of the code here. I'll just point out anywhere that I'm doing something different from the past or I'm doing something specific to bloom. Let's skip over everything and jump right to the end. There's a setup phase where we create the programs and other resources that we need, and a render loop phase that happens every animation frame. We're going to use floating point textures here. So before we create any textures, we need to load the xcolor buffer float extension. During the setup phase, we create our 5 programs plus a 6th for debugging when needed. Create Geometry Renderer is responsible for creating the geometry and managing all of its state. It returns a draw function. Call that and the program will update the geometry and render it to whatever frame buffer is bound, or to the canvas if nothing is bound. All of the other programs are slight variations of the exact same quad rendering program. The only difference between them is each has its own fragment shader. Each may have its own special setup process, usually to set uniform values or grab uniform locations, and each may have a special render pass process, mainly to set uniforms and scale the viewport. These functions do all that. They create and initialize the program, and they all return a draw function that performs the render pass, whatever that render pass does. Create Threshold Renderer sets up a program for extracting and rendering the brightest parts of a texture. Create Downsample Blur Renderer sets up the program for handling the downsample passes. Most Bloom implementations that I've read go through the entire set of passes in a single loop, but I'm doing them explicitly one at a time here just to make the process extra clear. Create Upsample Merge Renderer sets up the program for upsampling and adding the downsample textures. It returns a function that's a draw call. That function takes 2 textures, the smaller one first that will get blurred, and then the bigger one second, and the destination for the draw call. And create Tone Map Renderer does the tone mapping and optional gamma correction. This function is highly configurable, but only by changing the shader code, which I'll show in a bit. There's a multi-sample frame buffer for rendering the geometry too, for anti-aliasing. I'm not doing anything funky here. I'm just using a function simply to keep this code easy to read. I'm also using a function to take care of the many frame buffer objects too. Here we just provide it with a width and a height of the output. We could also provide a storage type, but I'm going to be using the same HDR-capable floating point storage throughout. That will be hard-coded. What we need back is more than just a frame buffer object, so this function returns a bundle of information which contains the frame buffer object itself, the texture attached to it. We'll write to that texture when the frame buffer object is bound and read from it later when it's not, and a couple of convenience values, the width and height of the output, which we can use for setting the viewport, and the width and height of each texel, which we'll use for the blurring operations. And that's it for the setup. Now, the render loop. We want anti-aliasing, so we bind the multi-sample frame buffer object, draw the geometry. It needs a timestamp to know how much to turn the model, and unbind. The color data is now saved, but in a multi-sample render buffer, and we need it in a texture. So we blit that to a regular frame buffer object with its regular texture attachment. And now we have an anti-aliased image in that texture that we can sample from. Next, the threshold program will extract the bright data that we need for the bloom. We're pulling from the geometry object's texture and writing it to the threshold's frame buffer object. Next, 5 consecutive downsample passes. The artifacts that you see at the smallest levels are from blowing the textures up so much. Because we upsample recursively, these artifacts will never show up in the final render. Next, 5 consecutive upsample passes. You can see that as we go, these colors would quickly saturate a regular texture, leaving us with a blown out white that's impossible to recover information from. That's what we're seeing now because I'm capturing the canvas, but the data in the texture is still full of valid, correct color detail. So the final step is to tone map. The end result that you see here depends a lot on the tone mapping algorithm that you choose. Here I'm using Uchimura with no gamma correction. I think it ended up working the best for this particular scene, but like I said, for other models and especially for photorealistic textures, you'll probably get better results from some of the other curves. I really hope this gives you a clear overview of what's going on here. Now let's take a look at the code that actually does all of this work. I'll not go into much of the detail here. I really encourage you to grab this code from GitHub and try it out for yourself. You'll need only an HTML page with a 480 by 480 canvas, and you'll need to figure out how to load GL matrix into the page yourself. There are no other dependencies or requirements. For the geometry program, I'm using an 8-color palette. At first it may look like a boring old texture palette, but the top color here is in HDR territory, and it's stored in a float32 array, not a uint8 array like we usually do. Because of that, the values here have to be normalized, so 0 stays at 0, 255 becomes 1, and everything else scales accordingly. And when we upload it to WebGL, we specify a floating point storage format and a float data type. And that is how you upload a floating point palette. All the other WebGL programs are variations of the same quad drawing program, so this is one of the few places that I'm using an abstraction. This function creates a quad drawing program. You provide it with an optional fragment shader, and it returns a draw call function. That draw call function is also incredibly basic. You just provide it with an array of textures and an output frame buffer object, and it makes sure everything is bound, does the draw call, and unbinds. Nothing else. So if your fragment shader has any other requirements, like uniforms, you'll need to take care of them yourself before calling this draw function and do any cleanup afterwards. The first thing to use this quad program generator is the threshold program function. This is its fragment shader. It measures the luminance, or the brightness a human would perceive, of the fragment texels and discards anything that's below that threshold. It's common to use smooth step here so that the edges aren't so abrupt, but for this particular model and this particular bloom effect, that's really not necessary here. Next, the downsample program. There are two important variables here, one for setting the texel size uniform for the blurring operation, and another for setting the size of the viewport to match the frame buffer object output. The fragment shader is really the only complicated part here. We take 13 weighted samples for a single pass bilinear Gaussian blur. This blur and the next one are really quite clever and not at all as complicated as they look, but it takes a while to explain. So if anyone's interested in a technical breakdown of why this works, let me know in the comments. And after that, the upsample program. Here again, we're using an unusual but much more common 4-sample 3x3 Gaussian kernel, and we're sending 2 textures to the quad renderer. The smaller one at texture 0 gets upsampled and blurred, and the bigger one at texture 1 is just sampled at its regular size. Again, we'll need a texel size for blurring the smaller texture and an output size for setting the viewport. And the tone map and gamma correction program. I've included a lot of different algorithms here. The one that I've found works best with this model is the Uchimura tone map algorithm from Gran Turismo. And that's it. It's not what I'd call super complicated. Each step is pretty simple. It's just that there's a lot of steps for this one effect, but it's worth trying for sure. A lot of really useful things to learn too. HDR and floating point textures, downsampling and upsampling, viewport resizing, tone mapping, and though we didn't do it here, color grading is a super powerful way of adding a unique style to your applications and maybe fixing tone mapping problems. So try out the code here and try implementing your own in a style that you like. Now, I'm not sure what I'm going to cover next time, but whatever it is, I'll see you then.